Okay, here is the brief review of exponential functions, and there is a lot to this. Like I said, this is very brief. But here is the definition of what an exponential function is right here. And what we want to do is actually take and take a look at what the basic graph looks like here. And so if I come over here, I noticed when I did this, I actually graphed, I have here B, but that should be the letter A. So excuse me for this. This would be like B to the X, where B is greater than 0, and, B is not equal to 1. Okay. So just let's look at this as a B here. And like I said, excuse me for that error on my part here with this slide. It's not really an error, but just, potential confusion. Okay, so essentially we got a real number here for our base function. So this would be what the graph would look like for an exponential function. That kind of makes sense, right? If I take 2 to the x, if I take x2 and square it, or the third power, the fourth power, you know that that's going to get really, really, really big. However, if I take a number in between 0 and 1, then I know if I take, 1/2 to the first power, I get 1/2, 1/2 to the second power, I get 1/4, 1/2 to the third power, I get 1/8, and so forth. Those numbers are going to get smaller and smaller and smaller. And essentially, exponentials with a base between 0 and 1 are going to decrease and look like this and actually run out to the, have the line y equals 0 as a horizontal asymptote. And likewise here too, if I put negative values in there, if I think of like 2 raised to the negative second power, that's the same thing as, 1/2 raised to the second power to get 1/4. And if I think of 2 raised to the negative third power, that is literally going to be like 1/2 raised to the third power, or 1/8. And you can see that I get closer and closer to 0 the smaller I go, or further I go out in that direction for x. So essentially what you got to remember here is that, they either go up when the base is positive, or go down, when the base is greater than 1. And if it's between 0 and 1, it goes downward. Now, it say right here in the definition, it cannot equal 1. Okay, so, and you can't have negative numbers here for a base. So again, we just look at that number here and we'll know what the graph looks like. So if I just jump real quick here into Desmos, and I have the graph, I'm going to turn that off, like graph like 5 to the x, you can see that that graph is going to go upward. And notice all these exponentials, right? Any number to the 0 power is just going to be 1. So we always have that point on the graph, no matter what the base is. I can change this to, say like a 7. I'll raise that to the x power. You can see that it's just going to look like that. And if I put a number, let's say, if I put a set of parentheses here, like, just get rid of that so we don't get the error. Say like 1/2. I was using that as a start all over again here. 1 divided by 2. And there we go. And I'll get out of here and close my parenthesis and then make an exponent here next. Notice again, it's still going to have that point here. And if I change my denominator here to like 1/3, again, that's a number between 0 and 1. Notice it's, again, still going to contain that point, but it's, if I trace this out here, I get really, really close to 0. Even like as I get out here to 7, it's really close to 0, but it's never going to equal 0, no matter how large x gets, even if it's like a million. It's just not going to be able to show that many decimal places to show how small the number is or how close it is to 0. So for what I'm going to be doing here, I'm going to change that back to 5x, okay? And know that you'll be asked to do things like, excuse me, I don't want that one here. I want these examples. Like this, identify what a graph looks like. So that's 1/4 of the x. That's just going to be the basic one. It has the y equals 0 as a horizontal asymptote. It's not going to go up. It's going to go down. That's my only choice here for a simple one. But over here now, notice we start messing around with the different parameters. And we did talk about transformations and specifically translations in the other video. So, what effect does this 4 and that negative and this negative have on the graph of 4 minus 5 raised to the negative x? Well, that's kind of what I have over here. My parent function is 5 to the x power. Okay, now again, I'm taking the x and multiplying by -1. I have a negative, not this negative is not governed by that exponent, but after I evaluate the power, my order of operations tells me then I multiply by the -1. So probably would be better to have parentheses here, but they don't in my math lab. So just understand that -1 isn't affected by this exponent. And then I just add 4 to the function. So that's going to, shift the graph up. So the idea is to pick, the proper graph here out of these 4 that match up with this. So knowing how this negative, and that 4 affect the function, we're going to come over here and look at this. So if I look at this particular example here, let me just come over here and do this. Notice this 4 would be equivalent to making k 4. So if I come over here and I shift my value, not c, excuse me. If I shift my k to be equal to 4, okay, and I want to be looking at this graph right here, all that does is shift the blue graph up 4 units when k is equal to 4, okay? So I got that, keep going back to that, excuse me. Trying to get back to, that's the one I want to get back to, okay? So I know my graph is shifting up 4. Now the negative would be the b here, and the c would be 0, okay? And that a would be -1. So that's going to be a -1, and that's going to be a -1. Okay, that'll get me the -1 out in front of x when b is equal to -1. So I'm just going to slide that over for b equal to -1. All right. And then I am going to make the a be -1. So I'm going to slide that over to -1. All right. Okay. So now you can see that red graph, what happened when the b was -1. When I went from 1 to -1, notice how the graph, flips over the y-axis, okay? Flips over the y-axis there. And so I am going to get that graph manipulated in that pattern. So I know it flips over the y-axis. Then this is going to flip it over the x-axis, okay? So I guess if I take a look at these individually, one at a time, if I change that back to 1, and I change this back to 0, okay, and I change that back to 1, notice the graph matches up, okay? So let's change the b, like we said, to -1. You see how that flips it over the y-axis, okay? And I'll change that back to 1. And then we said if we change the a to -1, watch how it flips it over the x-axis. Okay, so if I apply all these things to it now, all right, as we said, the b is going to be -1, the a is going to be -1, and the k is going to be equal to 4. I'll shift that over. That's going to shift that up 4 units. And we take care of both of those flipping over both the x and y, which can be a little bit confusing. We know we get this graph right here. Okay, so just to double check here, I have the original function here, and this is in black. And if I click on that, notice that black graph matches exactly with that red graph. Okay, so all I did was manipulate this function right here, this y equal 5 to the x. By taking these values here, these parameters, and plugging in numbers, I get equations like this, which again, you're just going to be asked figure out what the graph looks like. So again, you can just punch in the black route, turn these all off, okay, and know that you can see that black graph here matches up pretty much with what we have here in graph C. Okay, so that's the one way to do it, but understand that what we're doing to get that black graph here again is flipping it over the x-axis, then over the y-axis, and then shifting the unit or the graph up 4 units. So that 0.01 should now be at 0, 3. Okay. All right. So there you have it. And not much else to say about that one other than that's how we graph these basic graphs. Okay. The other thing I wanted to mention here is how to solve some functions that are basic exponentials. Okay, so I have here some of the other ones I taught in the classroom when we had some more time, but I just picked a real simple one here, number 3, to solve for x. One technique to use to solve exponential functions, because we have an exponential equation, we have an exponential function within that equation, is that we try to get the bases to match here. Okay, so I know obviously 7 is a prime number. I can't break that down, but I can write the 49 as 7 squared like I do over here. Therefore, since this is actually a one-to-one function, what I can do is just basically, since these bases are the same, I could set the exponents equal to one another, and I end up with x equal 2, and that would be the solution for that equation. All right. Now, ones like 4 and 5 are a little bit more complex. What you would actually have to do here is when we have a power of a power, you would just, I'm not going to work this one out because I'm going to do something similar down here, but just multiply the 6 times the x plus 9, and you would get 6x plus 54, and then you would have negative 3x equals 6x plus 54 because the bases would be the same, and that is the number e, which is about 2.7182, and we'll talk to that where that number comes from a little later. This one here, again, 64 and 16, that can be broken down as a power of 4. So I'm going to write the 16 as 4 squared and then leave my exponent as x plus 1. And I'm going to write the 64 as 4 cubed, and then I'm going to leave my exponent as 5x. So I just threw in a couple extra set of parentheses here. I could have wrote the third power just like I did over here, but I did it both ways. Now I multiply, remember I have a power of a power, I multiply the exponents. So 3 times 5x gives me 15x. 2 times x plus 1 after you use the distributive property gives me 2x plus 2. Now I have powers with like bases. And so therefore I set the exponents equal to one another. 15x equals 2x plus 2. Subtract 2x from both sides, divide by 13, I get 2/13, and there we go. Remember, make sure you enter your answer here. Pay attention to what this says. You have to type in an integer, which you can't. That's not the solution, or a fraction. If you typed in the decimal equivalent, it's going to mark it wrong. Okay. So again, that is how we do. I mislabeled that. That's actually number 5. Sorry about that. That's this particular equation, obviously. So that's where we get the 2/13 here for question number 5 here that I had listed on this slide or PDF document. Okay, so again, that video there just dealt with some basics of graphing using Desmos to graph. Most of you are probably going to opt to, when you see stuff like that, just, it says graph it on paper, then choose the correct one on the right. I mean, just mentally know what these are going to look like, and you should be able to pick them out here. But probably a good idea, especially ones like this that are more complex, to, come over here and put them in Desmos here. Let me just turn that off and know that I can just graph that here and match it up. I mean, that's pretty obvious way of doing that, and I'm sure most of you will do that, but I still think it's worth knowing what the graph should look like first, and that knowing exponential functions are going to be ones that, the parent functions, real simple here, when we have a positive number not equal to 1, it's either going to look like this when that positive number is greater than 1, or it's going to look like this, go down when we have a positive number between 0 and 1. Okay, so that's that concept, and we will be back with another video dealing with some more exponential functions and equations.